interstellar objects, objects that come into the solar system from outside, similar to 3i Atlas, that look anomalous.
There is a bright streak across a small backyard sky, a silvery halo, a backyard telescope trained with shaking hands, a phone camera that won't quite catch the detail, a scientist at a laptop, eyes tired, scrolling photometry one more time. A single sentence changes the room. October 29th, someone says, and then it vanishes behind the sun. What happens when the most important moment in a comet's life occurs blindfolded? What if that moment decides whether a visitor leaves us or stays? This is the question pressing against the glass tonight. This is the story of 3i Atlas and the provocative claim from Avi Loeb that it may not leave the solar system. The mainstream view is clear and steady. Most astronomers say it looks like a comet. Comets are messy. They sputter. They fragment. They surprise us. We have seen stranger things than we expected. Point the telescope, collect data, update models, repeat. Science step by step. But sometimes data pile up into a pattern that does not fit the neat model. A number here, a ratio there, a geometry that keeps repeating. Those clustered oddities ask to be taken seriously. Avi Loeb listened. So did a handful of others. 3 facts anchor the debate. First, the date. October 29th, 2025. On that day, 3 Atlas will reach perihelion, its closest approach to the sun, and from Earth it will slip behind the solar glare. The geometry is brutal. Earth, sun, and object in a line. For nearly 6 weeks, most telescopes cannot look. The data gap stretches from late October into early December. We lose direct sight at the single moment when the comet might change its fate. Second, the size. Early brightness measurements, corrected for distance and angle, point to a nucleus on the order of 20 kilometers across. That's not a pebble. That's not a rock the size of a car. 20 kilometers. Imagine a city-sized chunk of frozen ice and rock. Estimates translate that brightness into a mass of roughly 33 billion tons. By interstellar standards so far, that would be colossal. It dwarfs the 2 other interstellar visitors we know. Those were tiny in comparison. Tiny enough to slip through surveys like shadows. Third, the paradox. Telescopes measured active outgassing. Carbon dioxide dominates. The ratio of CO2 to water sits near 8:1. That chemistry is odd. For most comets in our solar system, water wins. Outgassing acts like tiny thrusters. When gas jets off the surface, objects nudge. We see it in the astrometric record. We expect slow drifts. We expect subtle curves away from pure gravity-only motion. But not here. Despite a reported gas production of 100 to 150 kilograms per second, the astrometry finds no measurable non-gravitational acceleration. The object follows a gravity-only path so closely that the usual cometary rocket effect is missing. That absence is not small. It changes the math. If gas flows that large were acting on a small nucleus, the comet would veer. It would show the fingerprint of thrust. So why does it not? Either the nucleus is enormous and dense enough that the same gas flow produces negligible acceleration, or the outgassing somehow cancels itself out. Or some say, an engineered or non-natural scenario is not yet off the table. Avi Loeb is careful. He is not shouting certainty. He points to the numbers. He says, the odds tilt in a direction that deserves scrutiny. Numbers have weight. They do heavy lifting in astronomy. Surveys like Pan-STARRS and the Vera Rubin Observatory scan the sky night after night. Models of object populations rest on what we already see. The simple statistical rule is small bodies are far more common than large ones. If the discovery pipeline is working, the first interstellar objects to appear should be the tiniest because they are the most numerous. But the record so far is 3 visitors, 2 small, 1 suddenly huge. That jump in scale strains the expectations. Population models say the odds of finding something this large before 100, maybe 1,000 smaller counterparts are tiny. Analysts run the numbers and feel the tug of a broken power law. Either we have been blind to a vast population of faint objects, which itself would be a huge surprise, or Atlas is an exceptional outlier. Add to that the orbital geometry. Atlas arrives nearly aligned with the ecliptic plane, tilted by only about 5 degrees. A random interstellar visitor should swoop in at a wild angle. Instead, it glides close to the plane where our planets orbit. It threads a path with a chain of close flybys. On October 3rd, it passes within 29 million kilometers of Mars. Later, it will come under the influence of Venus, and then, months later, Jupiter in March 2026. 3 near misses in series. The odds stack against coincidence. Imagine a stone skipping across a pond. Each skip is a gravitational handshake with a planet. Those handshakes can nudge speed and direction. They can, in principle, set up the single critical moment at perihelion. At that moment, physics is unforgiving. A tiny change in velocity, a few kilometers per second, can tip the object from an outbound interstellar trajectory into a bound, captured orbit. That is the stake. If the object receives a delta V at perihelion of order kilometers per second, it could be held by the sun. If it does not, it will sail away on a long, lonely arc back to interstellar space. We will only know which way it went when it reappears months later, when the blackout ends. So why can't we watch? Because the sun blinds us. Telescopes on Earth cannot point safely close to the solar disk. Space telescopes like Hubble and JWST have strict sun avoidance rules to protect their optics. Even if they could point, the glare would swamp the faint light of a small, fast-moving object. Only instruments built to study the sun can look there. Coronagraphs, solar probes, tools made to chase solar storms, not comets. Those tools have seen comets before. SOHO's coronagraphs find sun grazers all the time. Parker Solar Probe's Whisper camera has imaged objects skimming past the sun, but these instruments are not optimized for faint, distant targets. Their sensitivity and cadence are limited. They are tuned to bright coronal structures, not a 10-kilometer ice ball hiding in the glare. Practically, the blackout is total for most observers. From late October to early December, the most critical moments will unfold beyond our direct view. Any sudden change of orbit, any engineered burn, any structural breakup, all of it could play out unseen. When the comet reemerges, we will read the aftermath in the orbit and in the chemistry. Until then, data will be missing from the central chapter of the story. Back before the blackout, telescopes did what they could. They took images, they took spectra, they tracked position. The first images were unsettling. Instead of the classic broad tail, observers saw a concentrated forward glow on the sunward side, a bright pancake of light that resisted corrections for smeared motion or instrumental artifacts. As the object warmed, a tail did form and eventually aligned with the solar wind. Yet that early forward glow raised eyebrows. Spectra carried their own surprise. Near-infrared measurements found CO2 dominating the volatile mix, carbon dioxide outpacing water by a large margin. For new arrivals from interstellar space, one explanation is preservation. Maybe the surface locked in CO2 ice, shielded from a star's heat for eons. Maybe the composition reflects a different birth environment. Calibration teams cautioned that early results were provisional. Still, the chemistry added another tile to the mosaic of oddities. Then, in late September, a sudden green surge swept the coma. Amateur cameras and professional spectrographs alike caught a bright green emission. Green often appears near perihelion in solar system comets, but here it arrived early and bright. The color trace points to molecules like C2 or CN fluorescing under ultraviolet. Why early? Why so strong? Each answer offered its own puzzle. The non-gravitational acceleration question is the sharpest blade. Comet science treats outgassing like a tiny rocket. Measure the gas, estimate the mass, see the acceleration, do the math. Most comets show the expected subtle push. Atlas does not. The Minor Planet Center logged thousands of positional measurements. The residuals are clean, no hint of drift beyond tight upper limits. If the measured outgassing is real, then something else must be true. Either the nucleus mass is enormous, pushing the expected acceleration below detection, or the jets are arranged in perfect balance. Every outflow cancels another. Or the observations miss a more complex reality, like a cluster of fragments whose collective behavior hides the acceleration. Each alternative strains plausibility in different ways. To reconcile the data, modelers run Monte Carlo simulations. They sweep through sizes, densities, jet geometries. They find that anything smaller than about 5 kilometers or less dense than typical water ice will not survive the contradictions. Only a truly massive, dense nucleus fits both the photometric and dynamical evidence without implausible fine-tuning. Avi Loeb frames the debate differently. He stacks the anomalies: mass, size, chemistry, orbital alignment, planetary flybys, lack of non-gravitational movement. Taken together, the cluster forms a pattern that, to him, calls for careful attention, not certainty, not a declaration of alien technology, but a request: do not assume the default explanation. Test the alternatives. Mainstream astronomers reply with steady caution. Tom Statler, NASA's small body lead, says, it looks like a comet. It behaves like comets. Others point to selection bias, to the patchy history of surveys, to the raw messiness of volatile, friable bodies. Comets surprise us. They have a wide behavior envelope. When claims of the extraordinary arise, the burden of proof is on the extraordinary claim. Both sides share a common language: data, prediction, test. The test is simple and falsifiable. If, when it reemerges in early December, Atlas's orbit and non-gravitational terms match the preconjunction solution, the natural model wins. If the orbit shows an impulsive change consistent with a delta V at perihelion, the debate shifts fundamentally. Either way, there's a clear, objective measurement awaiting us. Imagine standing on the edge of a stage. Backstage, a player moves. The curtain drops. For 6 weeks, we cannot see what happens. We can only watch the footprints left on the floorboard when the curtain rises. Those footprints will be orbital elements, composition shifts, brightness changes, rotation variations. They will be the forensic evidence we read later. Why would anyone suggest an engineered maneuver? Because the numbers allow it. Because capture is physically possible with a single well-timed push at perihelion. Because a mass this large, combined with negligible acceleration under observed outgassing, invites alternative explanations. Because the flight path hugs the ecliptic in a way that reduces the randomness expected from interstellar arrivals. Theories multiply, natural ones first. A massive, dense object born in another star system might preserve unusual volatile ratios. A surface crust of CO2 might shield deeper water ice. Spin or shape could distribute jets symmetrically. A swarm of fragments might mimic a single coherent body. Statistical flukes happen. The universe sometimes hands us unlikely combinations. Alternative ideas press harder. What if the object carries internal mass that reduces acceleration? What if a hidden mechanism controls thrust? What if an engineered delta V at perihelion alters the path? These ideas push us into speculative territory. They require evidence beyond anomaly stacking. They require a measurable change in orbit or other compelling signatures. The stakes are high for one simple reason. Capture means the object becomes a long-term resident. A visitor that stays changes our long-term access. It becomes an object we can study year after year. It becomes a target for missions. It rewrites part of the story of interstellar exchange. And if we found evidence of non-natural alteration, that would be a discovery that reorders scientific priorities. But discovery demands care. The scientific method is the guardrail. Make a prediction. Wait. Observe. Compare. Reject or accept. That is the path both camps ask us to trust. Avi Loeb asks for attention and rigorous testing. Mainstream science insists on patience and skepticism. Both want data. What will we watch for when the comet reappears? Orbital elements first. A change in eccentricity, energy, semi-major axis. Any shift beyond preconjunction error bars would be the clearest sign. Non-gravitational terms next. If an impulsive push occurred, residuals will show it. Spectra. Will CO2 dominance persist? Will water rise? Will new species appear? Brightness and morphology. Fragmentation, a brighter or dimmer coma, a changed tail. Rotation state. Did torque alter the spin? Light curves will tell. And later in March 2026, the Jupiter encounter offers a second test. Jupiter's gravity will either confirm a captured orbit or act as a second doorway to interstellar exile. The months after reemergence will be crucial. Telescopes worldwide will watch. Surveys will tune their cadence. Amateur astronomers will point their cameras. The entire community will read the handwriting left in the stars. There is elegance in the restraint. Science does not leap to the most dramatic explanation. It lines up hypotheses, sets tests, and waits for the decisive data. That waiting is the hardest part for a public hungry for answers. We want a verdict now. The universe, with its slow clocks, will not oblige. Sensory images matter because they humanize the math. Picture the comet as a silvery coin in sunlight, spinning slowly as jets hiss from its flank. Picture the sun as a blinding furnace that swallows the light and leaves us peering into darkness. Picture backyard observers with steaming cups, cameras on tripods, watching a live stream and refreshing the feed. Picture a control room where scientists hold their breath at a rising curve on a plot. These are the tiny human touches that anchor a cosmic argument. Short expert lines can cut through the fog. It looks like a comet. A careful paraphrase of a survey scientist. Our models expect many small objects, not a sudden giant. Avi Loeb, when anomalies cluster, you test alternatives. Keep the quotes sharp. Let them be hinge points. They show the disagreement without turning it into theater. We will not claim certainty today. That would be the wrong kind of story. Instead, we hold a sober question up to the sky. What are we missing during the solar blackout? What did it mean that Mars had a near pass on October 3rd? What did the forward glow tell us about internal mechanics? What changed at perihelion when no camera could look? When Atlas returns, the answers will be written in numbers. The orbit will whisper what forces acted. The spectrum will sing the chemistry of its surface. The light curve will narrate rotation and breakup, and the global community will triangulate the truth from those signals. If the orbit stays steady, the natural comet model gains strength. The anomalies will remain intriguing footnotes. We will refine models. We will revisit population statistics. We will learn more about interstellar diversity. If the orbit changes in a way consistent with a perihelion impulse, the conversation will turn. We will need more data. We will need missions. We will need to ask new questions about how such a push could occur. Either way, the story is a triumph of method. A claim is made, predictions follow, observations will decide. That is how science loses bias and gains truth. Imagine the moment in early December when the first fresh astrometry arrives. A team at an observatory submits positions. The FIT updates. A graph spikes or remains flat. People on both sides of the debate watch the same plot. Their faces reveal hope, relief, or an inward shrug. The universe gives its answer in quiet numbers. Our cameras and probes may have missed the act. We may have missed the fireworks. But nature leaves a ledger. Orbits are records. Chemistry is a record. Brightness is a record. We read them like a detective reads fingerprints. Tonight, the sky holds its secret behind the sun. For 6 weeks, the stage is empty. For 6 weeks, the players move out of sight. We wait, we measure, we prepare to be surprised. So here's the simple, urgent question that will pull us back to our screens. When 3i Atlas steps out from behind the sun, will it be the visitor that leaves us in the night, or the one that decides to stay? Will the orbit read as escape or as capture? That quiet, testable split is the hinge of this story. Keep your eyes on early December. Keep your ears to observatory updates. We will not know the verdict until the data speak, but the debate has already done its work. It has sharpened what to look for. It has focused the questions into measurable outcomes, and that is where the real drama lives. Not in speculation, but in the patient, precise measurement of the sky. Not in certainty, but in the willingness to follow evidence wherever it leads. If you want to keep watching, we will meet again when Atlas reappears. We will look at the new orbit. We will read the spectrum. We will weigh the evidence. Until then, the sky holds a secret. The sun guards it. Science waits with a steady hand. The question remains, will 3i Atlas leave the solar system, or will it become at last our celestial neighbor?